feel free to reach out. Feel free to reach out to me as well with questions on the normal fault assignment. Take a second for the computer to get to the objective. Okay, so I showed this picture before. I just like it. It's a beautiful picture. We don't get flowers that often out in the desert, so it's pretty nice. So this is sitting on top of the Fairview Peak, 1954 scarp. So I thought I'd show it again. So today, what I wanted to do is just keep exploring. Everyone hear me okay? Everyone see everything okay? Thumbs up? Okay, good. Keep exploring normal faults in the basin or range. And just so what I'll cover today is just I'll revisit the basin range just really quickly to get our heads wrapped around it. I'll show some more mapping of normal faults, so just some more examples of different geomorphic features, things that we see that indicate areas of active faulting. And then if I have time at the end, I'll talk about assessing paleoseismic parameters based on these mapping observations and talk a little bit about what we use it for. So just starting out to get us back to the basin and the range, the region between the Sierra Nevadas in California and the Wasatch in Utah. It's about 800 kilometers wide, a zone of mountain and basin topography, which is the result of extension across normal faults. And so I'll zoom in here, a little color image on the top there. I mentioned a few historical earthquakes last time. Those are shown in yellow. So the ones in Nevada there, just to the right of the red star, is the Central Nevada Seismic Belt. So it's a relatively continuous belt of earthquakes from 1915, 1932, 1954, all in the magnitude 7 range. So it's really a quite interesting conundrum in the basin range, and why would they concentrate along this zone along strike, where there's so many other active faults that make similar belts in Nevada. So it's kind of an ongoing academic question is whether similar belts have exhibited activity closely spaced in time in the geologic past. So I'm going to talk about some of these. So this is a blow up DEM down here on the bottom. I'll show some examples from the Butte Range over here in the east and the Egan Range over here in the east. I think I have some examples from the Simpson Park Range here, sort of in central Nevada. I showed this one last time, so I'm not going to spend much time on it, but it's good to just zoom your eyes in again on this region here in the central part of this geologic strip map along the fault. You notice there's some red faults out here in the Piedmont Slope region. So the slopes going to the east, alluvial fans coming off the mountain, and there's the faults mapped in red out here in the Piedmont Slope. So I know I showed this last time, but just really clue your eyes into the old alluvial surfaces. So in this uninterpreted image over here, the deeply dissected surfaces are relatively older than surfaces that are somewhat smooth, with sort of flat surfaces between drainages with less incision. And then the younger ones have this sort of downstream spanning shape to them, and they extend up into the older surfaces. So that's seen in this interpreted image over here, where the green is the old, the brown is the intermediate, and the yellow is the young. And then of course the faults are cutting across here, and so often we notice the faults where they preserve an older surface above them. But that's not always the case, as I'll show in a little bit here. And then faults in the intermediate surface are kind of difficult to see on the uninterpreted image over here, but if you look really closely, there's little light toned lineaments that go orthogonal to the drainage direction. So that's how one of the ways we recognize. I talked about this example last time too, but it's also really a really good example of showing progressive deformation on the different age surfaces. And I'll show a couple images. So this is the Egan Range, which is along the left side of this DEM here on the left. This is the full strip map, which is too small to really see the details. So I've blown up this one little section here, which is sort of sits where there's this step in the range front across the Piedmont Slope to another range front. So it's a big right step in the system. And so this is a zoom in, and I'll show it again in the next slide. And so in this way, I've turned it so that north is now to the right side, which makes it a little easier to see the different deposits. I've also turned the image the same way. So we're kind of looking from the valley towards the mountain front. So the mountain front would be this kind of light green color, which is the topo map, the base map. And here's the unit mapped in here. And I'll just bring your attention to this red fault that's mapped here on the bottom. And it's also mapped here in black on the image. And so the thing to take away here is that there's about a 2-meter scarp in this brown unit here, which is right here, which is mapped as an intermediate age surface. And you'll notice that the drainages are not very well developed. They're there. There are some drainages incising into the surface, but they're small. And then when you move to the right, the scarp becomes about 10 meters high, and it's preserving this older fan unit above the fault, which is mapped here in green. And then when you go a little bit further, the QTP mapped in purple is a pediment surface, which is basically an old fan surface that's been sort of denuded, and there's only a little lag of fan material on top. It has like a bedrock surface beneath this lag gravel. So essentially a very, very, very old alluvial surface. And the scarp there gets to be about 30 or 40 meters. And then when you go further to the north, it's juxtaposing bedrock against the alluvium. And so it becomes sort of a range front. So you can see the progression of ages of surfaces, and it just illustrates the progressive deformation. So there's more deformation, or more extension and down dropping of the valley adjacent to the old surface than there is in comparison to the intermediate surface. And then finally, the young surface doesn't have any faulting on it, so it just gives us a constraint on when the last event was. And again, just stop me at any time. I'm sharing my screen, so I can't really see the chat. So if somebody wants to yell out and stop me, that's perfectly okay. So this is the same thing. I just wanted to point out that it's really nice to use different data sets. So in the previous slide, I was showing a black and white aerial photograph. And then this is a Google Earth image. And so we can see sort of different things in these different images. So I encourage you to use, different data sets when we're working on these things. But again, here, if you look at the right, it's sort of orange color, it's sort of this bedrock. And then there's this deeply incised pediment, a pretty deeply incised old fan surface, and then a sort of moderately incised intermediate surface, and the fault running along the front. I just want to show you some different examples of how we see these things. So the Butte Range, again, there's a strip map on the left. It's a west-facing normal fault. The strip map's really too small for you guys to see all the details, but I'll zoom in on a few areas here in a second. The middle is an aerial photograph, showing the bedrock on the right side. And really prominent, when I first started talking about normal faulting, I mentioned that there's landforms in the basin range related to pluvial lakes, which can give us a really good time constraint. Ramon mentioned climatic drivers and different landforms associated with different periods of time. So we know basically that these, the high stand of this lake, these sort of concentric curvilinear shaped lines going across the image, was about 13,500 years ago. And the high stand was sort of, the waves of the lake were lapping onto this geophyte surface. Here's a picture of a scarp, about 3.5 meter scarp. So the fault runs right along left to right across the image. And this is again, getting back to that notion of there's not a whole lot of places where we can find scarps like this when the faults are constrained along the range front. But when you can find places where the deposit goes up past the fault and into the mouth of the canyon a little ways, sometimes you get these preserved little triangular shaped in plan view pieces of the alluvial fan preserved on the footwall. And then there's a scarp separating it. So in this example here, this is the scarp in the picture, and that's right down in here where my cursor is on the air photo. And so there's this sort of broad geophyte fan that's been incised by this younger alluvial surface, And then above the fault, and I didn't map out the exact extent of this, but above the fault, there's this little triangular piece of the QFI above the fault there. And so we can find the start there. But when you're mapping normal faults, you may only find a feature like that in several locations along the fault where the intermediate fan is big enough to be sort of extending up into the mountain range to the other side of the fault. So in some of these big strip maps, there may only be 3 or 4 of these sort of preserved fan remnants in the mountain range. Okay. So here's an image, a Google Earth image, and a topo map of the Butte Range. And again, I've rotated it so that the north is to the left, so that we're basically looking from, well, we're looking straight down at these, but essentially I wanted to give you a view like looking towards the mountain range. So the faults are going sort of left to right across. So when we start out, we don't know where the faults are, but we want to start looking for features that are prominent that may indicate something. So when I'm looking at this image, I see this little dark line right here, just like a really steep slope. Okay. I also noticed that there's kind of tall or high topography here, which is actually bedrock, and you can see that in the sort of the green in the topo map, with, tighter contours. So we have this sort of bedrock that's sort of coming across the image and then sort of bending away. And then we notice over here these deeply incised surfaces. So I was showing you examples of that previously. So we have some old fans over here. So we have a zone where there's a bunch of old fans. But then when we look over here on the left, there's a zone where we don't see that same sort of topography. So I'll show some close-ups here in a second as well. But sort of some smooth fans on this side and really deeply incised fans on this side. We have some sort of change going on, and we're trying to figure out what that is. The other thing we noticed is sort of this curvilinear trace right here, where it's dark brown below and some incised fans above. Remember, there was a lake in here in this basin. And so we have an interplay between the faulting and the lake shoreline, and I'll show an image of that in a second. The other thing we noticed is this sort of dark toned liniment that comes through here. I'll show the zoom in on that in a second, but that's something that's going sort of at an oblique angle to the drainage direction. And so that's something my eyes will clue into, like, okay, what's that? All right. So I'll zoom in right now to this area that I was just talking about, which is deeply incised fans and this sort of feature that cuts across them. And so when we look really closely at an aerial photograph, there's some bedding in here. And I think this image is a little grainy because it's a photo of a photo. But so there's some bedrock up here along the top, and sort of trending left to right, the bedding. And then it sort of transitions into sort of incised bedrock, transitioning into fans. So you can kind of get a sense that the topography is flattening out a little bit, sort of right in this area here. So you have this sort of developed drainage pattern in the bedrock, and then these sort of headwardly incising drainages in these old alluvial fans. And then what you notice is this dark band coming across here, and the preservation of this old surface right here on the right center of the photo above this liniment here. So that's a fault. But you also notice that it has another side to it. So essentially what it is it's a little graben cutting across here. And it's outboard of the range front, so it's out in the basin. And then coming over here, it continues. And so what you can notice is sort of a dark tone here facing to the bottom of the photo, and this lighter tone facing to the northern part of the photo. That's the light catching this graben feature here. Okay. Another thing to notice is that there's this darker unit here. So oftentimes we isolate an old alluvial fan by down dropping the hanging wall, and then younger fan material gets deposited and starts to bury the hanging wall. And so in this case, this would be an old fan, and this is an intermediate fan here. And what you notice is there's a little liniment cutting across that right at my cursor here as well. It's much smaller than the liniment going across and isolating the UFO fan. But what that suggests is there's been a younger earthquake associated with this smaller scarp, and so this intermediate fan has also been affected. Okay. And then here's pretty neat. Here's these shoreline features, these beach berms and stuff associated with the lake down here below. And then the real white stuff is the young fan. Okay, so we use tone and color a lot to differentiate different ages of the fans, and we also use cross-cutting relations and the various heights of the scarp to sort of help us now. So here's this is interpreted, and the lines are on the image on the top. That's kind of difficult to see, but it's shown here in the colors. And so, so I've mapped this sort of graben feature cutting across here, and this is sort of a quick and dirty map as part of a field mapping class. So here in the orange is this intermediate fan that's cut by the fault right here, and it extends up into above the fault a little bit. So if I go back, so that's this region right here where you have this old fan preserved, and then you have this intermediate fan that's kind of incised through it, and it's been also cut by the fault. And so that's shown here with this relationship between the green and the orange. Okay. So next I'm going to look at this area here. So we talked about these old fans. There's not really a range front, and you notice how it's kind of a curvilinear contact between the old fans and the bedrock. It's not a sharp range front fault trace, and that's just because the fault is sort of outboard of it in this location. And the blue again is where the shorelines are. And so it's interesting. There's a shoreline feature here. There's some high topography right here. You'll notice the bedrock comes down almost all the way to the basin. And I noted earlier this real dark shape. This real dark tone right here is a real steep area of the topography. So the lake comes right up to that steep zone. So we have to figure out how we're going to get this fault along the range front. And so we're going to look at some more detailed mapping where it's closer to the range front here. But there's places where it may be modified by the lake. The lake elevation came up right through the fault space. So here's an image of this region in this other box here. And so in this case, I've mapped these. I'll show a colored version in a second, but here's these shorelines have this dash X. Young fans come out of the canyons and the mountain and spread out here. And then you have these fans that still maintain a pretty good fan shape, but they've been buried by lake deposits. And they have some channels in them, but they're pretty weakly developed. So I mapped these as QFIs. And then the fault is along the range front. And there's places where the fault captures a scarp in a QFI surface where it extends up into the mountain front. So again, that is a key observation. So the few locations where fans extend into the mountain front are often cut by the fault. And there should be a bunch of question marks in here in places where I'm not really sure. But here again is another little triangle of orange above a fault trace where this fan was cut. And so essentially it's along the range front for a lot of it, cutting some of these younger intermediate age. So this is just to demonstrate how the mapping can help us figure out where the fault is based on the different ages of so I mentioned that really steep region, and that's a zone where the fault is difficult to see. But basically, we use our thinking cap. We have a big graben in the south. We have a range front trace in the north. Somehow it's got to get through there. And so the thinking is that the fault trace is somewhat varied by lacustrine deposits, and it's basically right up against the bedrock. So steep range front going down to the basin down below. And if you're really lucky, I've only found this one time really, there's actually slicken sides that are oriented in the normal direction on some fault planes right at the base of that slope. So to summarize that, I'll go back to this guy here, where we have a graben sort of out in the Piedmont that's affecting some old fans. It has some sort of step, or some sort of step maybe to the left, where it's going along this really steep bedrock face. So photographs I was just showing. And then from that bedrock trace, it stays along the bedrock Piedmont contact cutting a few intermediate bands to the north. We have this sort of different expression of the fault, depending on whether it's in the basin or along the range front, and different preservation of deposits. Here again, it's that scarp. With the bands for scale, just to show how awesome it is to geophyte surface cut by that. So here's another example from the Antelope Range. It's the west-facing normal fault. It's affecting a bunch of intermediate bands along this southern part. And then in the northern part, it's just separating an old pediment from the basin. So the scarps are larger in the northern part than they are in the southern part. So here's a photograph of Wiley Creek, which is right here. This is one of the few locations where the fan extends up to the east of the fault trace. And the interesting thing here is when you do detailed profile work, we're doing a little profile with our homework. But when you look at the slopes of this scarp, and here's a drawing of it down below, there's actually two surfaces reserved on the top. So I've named them QFI A and B. So sometimes you have to differentiate if they're really close or similar in age, but distinctly different from young or old. We can sometimes divide them up. So what's interesting about it is there's QFI A and B. They're only about a meter different, but the scarp is different heights across each of those surfaces. And then there's the scarp itself is over steepened, which is this sort of line along the bottom of or the middle of the drawing. So that would be the most recent event. And so essentially by just looking at the slopes of the scarp, we can interpret three events at this site. So QFI A has been uplifted by all three. QFI B is just by two of them. And then both of those surfaces were accentuated in height by down dropping across the most recent event. Okay, so I think this is the final map example I have. This is the Simpson Park Range. And it just shows another nice example of the different scarp heights and the different preservation of different age surfaces. So this is a blow up of this box here in the middle. I apologize, it's a little bit blurry. But what you can notice is the green colors are old fans and the brown colors are intermediate fans again. So if you look at the air photo on the right side over here, in the upper right corner, you have these deeply incised bands. On the bottom right corner, you also have these deeply incised bands. So I'll call your attention to the bottom corner here. This dark shadow along here is like a 10-meter high scarp that's preserving this old fan in the footwall. And then it's been incised by an intermediate fan, this brown unit, which cuts across here. And the scarp is smaller, okay? It's like 2 or 3 meters here. And then the blue is shoreline. So again, this lake basin that had a lake in it, in the lake Pleistocene. And the scarp then, if you use your eyes and follow the black arrows, cuts across some of these fluvial beach features with a scarp that's only about 1 meter high. So again, we have this progression of larger scarps with older surfaces, intermediate sized scarps with intermediate surfaces, and then the smallest scarp associated with the most recent event in the younger surface. Okay. Bell Creek Range. I won't talk a whole lot of details about this, but here's just another big QFO surface here. So there'll be a fault along the base of it here. And it sort of steps, and there's some little scarps here in the intermediate surface that are really hard to see in this particular image, so I won't spend a whole lot of time on it. But definitely an old surface here that's preserved above the fault. So here's a little diagram. So all of these maps were kind of conducted to try to get an idea of the amount of extension across the Great Basin. So this is just showing faults across the x-axis and years, and the different dots are different evidence for events along these faults. So this is along the range front in the Sierras and going into western Nevada in green. And this is the range front in the Wasatch. And so what you just notice is there's a lot more events along the Wasatch and along the Sierras where we're working for our homework than there are in the central part of the Great Basin. There's a lot more time in between events. So tens of thousands of years in some cases, 5,000 years or so. So the recurrence is a lot longer in central Nevada. And so I went through and I looked at all these ranges and mapped them and tried to get an idea of the offset based on slope profiles and things in the field and in imagery. And made some assumptions on the ages of these surfaces to get an idea of the extension rate. And what it turns out, basically, if you look at the intermediate age surfaces, we estimate their age around 50 to 70,000 years or so. Basically, you come up with an extension rate of about 0.8 millimeters per year if you add up all of these across the central part of Nevada, which is pretty similar to geodetic rates, modern custom velocity rates measured by GPS. So that's kind of cool. It just shows that we can use the geology to sort of confirm the extension rates going on in geodesy, which feeds into earthquake hazards. Yeah, I have a few minutes left, so so I wanted to just sort of talk a little bit about how we think about normal faults in exposures, how we think about the number of events, how we think about the age of the surfaces and things like that that all feed into sort of an analysis on the slide I just showed previously. So here on the left, it's just colluvial facies related to scarp degradation. So you produce a scarp, and then through time, the erosion from sheet wash and collapse of, well, a free face is just a straight vertical standing scarp. So you either get collapse of that through time, through toppling, but you also have sheet wash that's eroding the scarp, and eventually it starts to deposit material at the base of the scarp, and you lower the slope through time. So the sharpness of the slope gives us an indication of how young the relative age of the earthquake. We use subsurface colluvial stratigraphy a lot in our trenching efforts. So this is just A through F. You have a faulting event, and then this colluvial process I was talking about on the left here creates this what's called a colluvial wedge. So a small deposit here at the base of the scarp. And if there's another event, that original colluvial wedge material may get downdropped a bit and open up a new sort of mini graben, if you will, along the scarp, which again gets filled up with colluvium, and the process repeats. And so this last one has the most recent colluvium burying two other colluviums beneath it. So when we do our stratigraphic studies, we look for these different contacts between different colluvial packages and use those to infer the age of paleo event. So I mentioned slope diffusion. We can use the scarp degradation. We can use the diffusion equation, which basically plots the position of a particle on the slope through time. And we can look at, if you know the slopes from profiling and an estimate of the mass diffusivity of the material, you can get an age, estimate the age of how long that scarp has been eroding, assuming a vertical scarp initial condition. So here's a 4 meter scarp along the Simpson Park Range. You do the modeling on that, it comes out to be about 9,000 years. Further to the north along the same scarp is cut colluvial lake shorelines. And so that age is consistent with that. Because like shorelines, as I mentioned, would be about 13,000 years. So it seems to work fairly well. I mean, it's rough, but it's close. And then along the Takima Range, this scarp, you can barely even see it in the topography. It's only about waist high. I'm a geologist here. It's about a 1/2 meter high scarp or so. And diffusion modeling of it comes out of about 55,000 years, so quite a bit older. But the younger scarp shows up really crisp and clear in the landscape in the field. The older scarp does not. This particular scarp in the bottom one, you can actually see an aerial photograph, but it is pretty subtle. Soil pits. So soils develop with time, and especially in Nevada, we get in arid climates, we get a lot of carbonate that accumulates. Carbonate comes from the fluvial lake basin, the playas. It flows around in the dust and then it gets incorporated on the Piedmont slopes in the soils, percolates down with rain and groundwater, and accumulates in V horizons. So we can use that. The more carbonate, the greater the age. And looking at all these, this sort of white unit here going across all of these. So these soil pits are all across central Nevada, starting sort of central Nevada and going all the way to eastern Nevada. And so these are clay percent versus depth profiles, and then the different soil horizons. So we describe the soils, and the red just sort of indicates the base of the carbonate. So what you see from this is that they're somewhat similar in a relative sense, the depth of carbonate development. So we can use that to sort of assume or infer that these QFI surfaces are of similar age as they're distributed across Nevada. So again, that gets to the sort of climatic drivers idea that Ramon was talking about, where certain landforms are indicative of a certain time. So trenching. Trenching is the other way we look at the subsurface. And so I'll just show a couple of images of that. This one picture here in the middle is neat. It's the Egan Range, and the fault shows up really nicely in the subsurface here. And the white are sort of different carbonate horizons in the colluvium. This one here at the bottom is the Coyote Range, one of those real dramatic ranges in Nevada. And so here's the fault here. You notice a little graben, sort of a mini fissure here at the base of the fault scarp that's filled, and sort of these colluvial units here. And so the dark gray is one colluvial package, and the light gray is the second one. So we can infer two events here. And then just here's some other examples of how the different ways that that normal faults are expressed in subsurface. So this one example on the top here shows sort of a graben, where there's the main fault here on the left, and a fissure associated with it, with the most recent event. But there's also these other faults here on the right side that bound the western side of the graben. And so the dark gray and the white are basically graben fill sediments. And then you can see faults coming up through the dark gray and the white. So each time there's an event, there's extension across here, and create a little basin, a little graben along the scarp, and it fills with younger material. And we can use that to sort of estimate that there's three events here, because there's three different packages of graben fill. Here again, three events. The Toya Range, this is more of the classic colluvial deposits. So we have the dark gray, light gray, and the black colors indicate the three different colluvial packages. And then here on low slip rate faults, where we just don't have a lot of events, this is just showing one event, a little fissure, a really kind of small scarp. It's pretty eroded, and just this little fissure. And here's just photographs of those. Hard to see what's going on in that one. This, you can see the fissure in this one pretty well. So I mentioned historical. I'm almost done here. We talked a little bit about historical surface ruptures in the last normal fault lecture. This is the Fairview Peak in Dixie Valley. Here's Fairview Peak photo in Dixie Valley here. I didn't really talk about some of the parameters last time, but the maximum displacement were 3.8 meters in Dixie Valley and 4.8 meters in Fairview Peak, so pretty sizable. The rupture lengths were 67 kilometers and 45 kilometers, so pretty long earthquakes. They're magnitude 6.8 and 7.2. So we do all this mapping, and the mapping's really fun. One of the more fun things that I like to do with my work, but it has other implications in that it helps us find locations where we can do the more detailed work that I was talking about in the last couple of slides. Has implications beyond just probabilistic fault displacement hazard. Knowing where the fault ruptures are is super important for infrastructure and for zoning, like what was done with Alpes Criollo stuff in California, knowing where the faults are. But beyond that, it helps us with seismic hazards studies to estimate ground motion, estimate maximum magnitudes and stuff. So I'll just finish with, we can go along the rupture. So here's the Dixie Valley rupture, worked by John Paskey, where he went along and he actually measured the offsets from 1954 along. So this is called a slip distribution diagram, where it's distance along the x-axis and vertical displacement along the y-axis. And so they're variable, but we can get an average displacement and a maximum displacement with similar plot on it in further. This is on the Fairview Peak rupture, and this is the Dixie Valley rupture. So both of them are there. And so there's been a bunch of relationships. I know you can't really read that, but it'll be in the, I'll post this online. There's a bunch of relations that have been developed between surface rupture length, average displacement, maximum displacement, and from these we can estimate magnitude. So we can sort of look at a certain fault that we've mapped, estimate what the average and maximum displacements might be in a future earthquake. So here's what some of these relations look like. Wait, don't look at that one. I want to go to the next one. So this is maximum displacement on the top versus moment magnitude, and average displacement versus moment magnitude. So these are compiled from data sets around the world. I think there's like 85 earthquakes or something in the data set. There's strike, slip, reverse, and normal earthquakes in these data sets. Normal faults are somewhat less represented in the data set. So doing this sort of work in Nevada, we're kind of increasing our knowledge of data that can be fed into these sort of models to understand average and maximum displacements and surface rupture length. And so what we're learning in this class is mapping faults. We're focused on probabilistic fault displacement, but we're really wanting to teach you guys how to recognize features to map these faults. And this is just sort of one of the reasons why it's important. So I'm going to go ahead and stop there because I want to open it up for questions, and I also want to give Rachel time to go through her presentation. So any questions, comments on normal faults? They're fun. They're sort of elusive sometimes, but if you start cluing into the things that you can see that help indicate where they are, you can get a pretty good idea where to map it.
So going through the reading a bit, it mentioned that trying to quantify like right lateral or left lateral motion along a normal fault, so like some oblique slip, you need a piercing point. But are there other geomorphic indicators, like a combination between strike slip indicators and geomorphic or normal fault motion indicators to help map oblique motion?
Yeah, it's a really great question, and it's really difficult. We know from historic earthquakes that there has been some oblique motion, and so places like Fairview Peak, there's a few little fan crests that you can actually measure the right lateral offset. The other thing in Nevada is, extension started, in the late Miocene, and the extension was generally like along the range front, so it's like perfect extension. But now when there's a component of right lateral motion that's being fed from the San Andreas system into Nevada. And so on a gross geomorphic scale, you can see that the faults don't always follow the range front. They actually bend away from the range front. They extend along the range front for certain distances, and then they bend away from the range front. So it's showing, so it's kind of the extension direction has gone from east-west to more this sort of northwest through time. So that sort of rotation of the stress field shows up in the geomorphology a little bit just by the fault traces bending out of the range front. But exact piercing points are really hard to find in Nevada, pretty rare. So yeah, I mean, to answer your question, there's very few piercing points that you can actually pin down the right lateral motion. And plus, it's moving really slow. So the rates of motion are slower than the rates of erosion and geomorphology. So it's not really preserved very well.
Maybe Rachel will go over this, but I was wondering, there's a lot of anthropogenic modifications in the mapping area for the homework. And I was wondering if we could go over that and like how you parse out what is a fault versus anthropogenic, because sometimes they seem like they cross over each other. And yeah, I don't know if Rachel, if you're going to go over that or not, but.
That's a good question.
Yeah, Rich can go
Go
for
ahead,
it.
Rachel. I just want to say, yeah, I do recognize that there are roads and things like that along the fault traces in a lot of spots, and housing developments and things like that. But the large scale geomorphology of where the range front is still there, and so you may use more dashed lines than solid lines. You know, so we talked about the range fronts and triangular facets and stuff as a pretty good indicator of where the fault is. I showed a bunch of distributed pictures of distributed deformation. So be sure you look in the mountains as well for other features. There's scarps. There's a lot of different parallel, subparallel scarps all through the area. So try to search around and find those. And I showed grobens as well that are maybe outboard of the range front. So think of stepping traces and looking for, they may not be continuous for super long lengths, but there's different steps in the system. And I just want you guys to like really use your eyes and search around for those scarps that are going oblique and drainage directions and things like that. But I don't know, Rachel, if you have anything else to add.
No, there were a couple questions kind of related to what you just answered, and that students wrote in the homework about maybe the scale of the grobens. The one that you pointed out was a bit smaller, but they're aware that there could be really large scale horse groben complexes. So how should they, what's the best way to identify them and scale wise?
Yeah, sounds good. I think, so here's one here, this little profile shows these little grobens, okay, and there's no scale on this, but grobens along the fault trace, they're going to be anywhere from 5 meters to 30-40 meters across or something like that. So Horston grobens, yeah, we have mountains and valleys all across Nevada. That's like the large scale Horston groben sort of feature. But local grobens along the main fault are really common, and so that's what I want you guys to be looking for, especially in the northern part, like these sort of smaller features. So as far as the map scale that you can see them at, you have to map the whole range, all the lineaments, all the fault lineaments you interpret along the whole range there through the whole area. So a scale of like, start at maybe 1 to 24,000 and maybe down to 1 to 12,000 or something like that. It'd be a pretty good scale to see those in. You can zoom way in and really confirm to yourself that that's what you're looking at, but look at it holistically across the whole area, and use that profile tool too, because this profile here on the bottom, if you draw a profile across some of these features, you should see something like that, right? And so if you have your LiDAR hillshade illuminated from one side, you should see a shadow on one side and then a sort of a lighter tone lineament on the other side. The light is going to be reflecting off one side and shadowing on the other side. So you see that sort of opposing colors with parallel lineaments. There's a good chance that you're in sort of that.
Would it be helpful too if they measure either side of where they think the extent the groben is, the slope would have to be similar, right? So it wouldn't be an opposing.
Yeah, I mean, that's a good idea. If they're cutting across a fan or a terrace or something like that, it should have a similar slope on both sides. Okay, so if you draw your profile with a longer length on the same surface, I know we're not mapping geologic units in this assignment, but in your mind's eye, you can sort of see where that unit might be. So if you do the profile with slightly longer length, you should see a relatively even slope coming down, and then where it may be offset by the groben, and then that similar slope on the other side.
Great. And there's a couple more like general questions about the deformation of faults and normal faulting as opposed to other ones. Why are fault traces more sinuous and more distributed and deformed as opposed to other faulting environments?
It's in some cases it's dip related. So if the dip is shallowing, so there's a lot of steps between different traces along a range front, and then also steps to other mountain fronts. And so when the fault sort of, when the deformation field migrates across these sort of pre-existing mountains, the dip may change a little bit. So if it's shallows, you may get more graben formation. If it's steeper, you may have just a range front trace and be less distributed. But then when the dip shallows, you get more distributed. Strike slip faults are, generally steeper dips, so they tend to be a little straighter. They do have steps as well, but a little bit of a straighter trace through the landscape. But there's some places where the dip's steep on normal faults, where it's a range front trace, it's very narrow, narrow zone, and it's really straight and linear for quite some distance. But I've seen in some of my examples, it's not always the case. You kind of see step all over the place.
Great. If any other students want to put out another question that they had written in their reading assignments, or you can always reach out to us after too if you think of one later.
And I will go through some of the reading comments that you guys turned in and see if there's anything else, but I haven't seen them all yet. I just got them this morning. I can reach out to you, through email or something if I see a specific comment in yours that I can help address if you don't want to bring it up now. And then Rachel, did you want to go over something else as well?
Yeah, I have another little mini GIR example to just kind of show, like, similar how I did to Kumamoto. This is an example from Kaikoura in New Zealand.
Yeah, that's great. And I will stop sharing so that you can share. And just so you guys know, we completely realize that we've had normal fault lectures here for several days, fitting in other things and accommodating Chelsea and Ramon's schedule. But the whole point of the homework is to not have information to start, and then we give you more, and then we give you more. So you can kind of look at it and just sort of think about it a little bit without knowing all of this information. But now I think you've seen a lot of different examples of normal faults and how they're expressed. And so feel free to reach out with additional questions. But yeah, just try to get it mapped. All right, so let me stop sharing. You should be able to share, Rachel.
Awesome. Okay, so this is an area in New Zealand, Kaikoura. This is on the South Island. And I'm gonna just kind of zoom out and show you guys the general environment. The mapping area was right on the coast. It's highly vegetated. There's kind of a lot of deformation. And I'm gonna just zoom in right here for you guys to show just like an area of interest for you. So I did the same thing similar last year. I made a pre-rupture map of the area. And when you guys get your main fault mapping assignments, you will have a lot longer to complete them. And so for the first couple initial ones, we wanted you to practice a different type of mapping to aid with the GIR and the subsequent fault mapping, whether it be the morphologic, the geomorphic, or the geologic, like quaternary mapping. So when you do get the main mapping assignment, it'll be up to you guys to figure out which type of mapping you would like to do to help you with the GIR placement. It could be a little bit of one, a combination of all three. And so when I did this one, I kind of wanted to do a little bit of morphology, a little bit of geomorphology when I did it. So I like to map out all of the drainages first and any anthropogenic alteration. I like to kind of mark out where the extent of the water is in totality. So I know that it's probably not going to give me a lot of information on that side. I'll map some of the ridges too. And when I start to kind of delve in a little bit more in the surface, you can see that a lot of the quality of the hillshade is diminished a bit by the vegetation. There is kind of like this flat line area over here that's prone to erosion. And you do have kind of a lot of smaller roads that are cutting in and out of the area because it's a farming community. But I'll just show you some of like the larger features that I marked out. I like to use polygons when I'm trying to map the extent of certain features. And it's up to you to decide like what you like to do for the main mapping assignments, whatever helps you guys the most. But along this area, and it could be a bit hard too, because it looks like there's a lot going on, but there's also like nothing going on at the same time right here. So you want to take some time before you start just like plotting things to make sure what you're mapping is actually the case. I saw this landslide right here, and then there are a couple of little depressions on either side along the same strike as the landslide. Because this is a reverse environment, there's going to be a lot less evidence for faulting as opposed to normal and strike slip. As you saw in the GIR tables, there's just kind of fewer features to go off of. So when you do find them and they are aligned on the same strike, it's a really great indication that there could be a fault there. But because for this one last year, yeah, I was just like, landslides will be a good indication. And although they are a modifier for the GIR table, when they are actually like aligned with where you believe the fault could be, it's a great indication of faulting. And then if I went to finish all this geomorphic mapping and I wanted to start placing some of the GIR features, I have them right here. A lot of it is going to be kind of the lower modifier stuff. I like to mark out where the proximity to the active water is, so I know that my confidence may lower in those areas, where the anthropogenic alteration is, where the roads are kind of cutting across or leading into where my proposed fault location is. I have erosion into the main like the main like flat area where the larger water and the rivers meet. Some vegetation lineaments, although if I turned this off, you could see that a lot of the lineaments just maybe prefer growth on one side of a ridge as opposed to the other. So the lineaments may or may not be a result of faulting. But it was pretty much along this area where I mapped out the polygon features where I found the most indication of faulting. So I have these set like the ponds, and then I have this, which I mapped as a scarp, would be like the only indication that there's a significant dip along the strike. And if I went to go to where I ended up doing my faults, I had just kind of one large primary fault in this area where I have the highest quantity of features with the highest ranking. I increased my confidence to strong. But as I get into these flatter areas, it follows the same strike, but it may not necessarily have any active evidence of it. But if I imagined that another rupture could occur, could it rupture through that same strike? And I'll continue the mapping line that way. And something exciting, yeah. Mm-hmm.
There was a question about what scale you like to map at. You know, you kind of zooming in and out a little bit. And
yeah,
I like to look at different scales for sure, but in general, you want to sort of zero in on a scale that's going to work for you. I think in the end, I like to map it like I like to go back and forth between 1 to 24,000 and 1 to 12,000 kind of, but you definitely have to zoom in sometimes. And I don't know how you like to go about it, Rachel, if you want to comment on the scale.
Mm-hmm. Depending on the area, if a lot of the features are really well preserved and they're larger, like in the normal one, you can tell the range front is the range front from kind of a larger scale. But if I'm trying to really suss out the feature, I'll go closer, like 1 to 5,000. Any closer than that, you won't, no breaking news is going to happen as of like what you're looking at. But like generally for like the larger stuff, if I'm mapping out the drainages and some of like the anthropogenic alteration and some of the other morphologic elements, I'll do 1 to 10,000. If I'm trying to get more detail as to the location of the feature, I'll go closer. But I do like to spend some time, like, yeah, like Rich said, a little further away because you want to get the larger context of the area too.
Great.
And a nice thing about this area too, after the course ended, was because we did pre-rupture mapping for the 2016 earthquake, we got shape files of where the rupture actually occurred. So we can compare how well we did with how well we did at anticipating the rupture. So if we look a little further at where the 2016 rupture occurred, you'll see that a little further up and a little further down where I'd mapped it previously, it matched up pretty well. There are still some traces where I missed, and you can kind of see how now there is like some lineament to them. But generally in this area, if you do spend the time to find the geomorphic indicators, it's just kind of like good proof to show that it'll help you narrow down the location. But again, it's like when it actually ruptured, these maps are showing where the surface actually ruptured. And so these things may not be visible in a historic hillshade or older imagery, but it is like a good indication of how well you can anticipate the earthquake. But it also shows that there is going to be just inherent uncertainty as to where it's actually going to rupture, regardless of how well your pre-rupture map is. But this was just another little example. This is a reverse area, a lot of vegetation, maybe not a lot of GIR features, not a lot of evidence for where the fault could occur, but when you do find them, you want to point them and place them, and it'll help you with your fault location.
It sort of predicted where the rupture was going to be very well. So.
I think that was, yeah, one of the better ones that came from the pre and post comparisons. If I showed you my Parkfield map, it would have been a really different story. So
Quick question on the homework fort. When you say, or I guess this is a question for Rich, you suggested looking at hillshades with sun coming from the west. Is that a 270 or a 90 hillshade?
I would suggest 270 and 90.
Okay, cool. I have those. Okay, cool. I just wanted to make sure I wasn't dyslexic.
Yeah,
Thanks.
yeah. No, like just opposite sides, right? So,
yeah.
And generally perpendicular to the north-south grain of the front.
Cool. Thank you.
Yep. And so we're kind of done with presentations. We figured we'd leave out a little bit early today. You know, you guys have stuff to work on, but you know, I'll hang out here and we can discuss in class, and I'll leave the Zoom on if there's other questions. But feel free to email me with questions as well. I should be on campus all day Monday as well. But you know, any questions that come up, be sure to email me. We can jump on the Zoom and talk about it, or just email back and forth. And then Rachel has office hours that she's posted as well. Correct, right, Rachel?
Yeah, they're on the main website page. So 9 to 10, and then the Zoom link is posted right there too. Yeah, and then just a quick announcement. We do have opposing spring break between Arizona State and UNR. And I'm not sure about the other institutions that are involved here, but you know, we're going to start working on our personal projects, and so there'll be some class periods where we don't meet because the other school is going to be on their spring break. But just sort of the thought is that you'll be continuing to work on your individual projects through this whole time frame. And then when we get back together, you know, we'll have peer reviews and discussions with groups about the mapping as we progress through them. But so I just want to make that announcement. The schedule will get a little weird for that. And then also spring break, daylight savings is coming up too. And I mentioned this when we're emailing you folks at UNR when we started the class. The class will meet an hour later once daylight savings. I think that's after March 13th. So it'll be 10:30 to 11:45 instead of 9:30 to 10:45. Because Arizona doesn't do daylight savings. So that's kind of
a little tricky, but I think we can handle it. I don't think anybody had a conflict with that. But so with that said, I'll hang out on the Zoom here till we're out of class time to discuss anything about the mapping. But please reach out with questions. You know, it's really meant to just try to find those fault traces best you can and play with the profile tool. And again, I'll say, I know we're not mapping geologic units, but thinking about the geologic units is really important. So there's places where there's, you know, fans, there's places where there's moraines and things that come out across the fault that are offset. They have to think about that a little bit. And then you also have to think about sort of why it's a little bit more distributed in one area versus another. And just remember, I was talking about it being very close to the Walker Lane, which is a right lateral strike slip area, but it's also a normal fault. It's basically on the boundary between the Basin Range and the Walker Lane. So you could have some influence from both. But how the fault is expressed and how distributed is sort of related to, like I mentioned earlier, dip and also tectonic environment. So think about that, and just get proficient at using the profile tool, because it will help you as you analyze things when you're doing your personal project. It's pretty simple to use and QGIS.
And then Isabella's question for, can we choose what sort of faulting we want to focus on? So I believe Chelsea has already assigned the students to the projects they're going to be working on. They based it off of your guys's the poll that you took about what experience you have or what areas you already have experience in. But we'll be releasing, or we'll be talking about like at least the first set of main mapping projects next week. So you guys will get a little bit more info about that.
Yeah, and there might be potential to sort of request certain faulting environments for the second project possibly, but we'll go over that with Chelsea. The first ones will be kind of assigned, but yeah, I mean, I know some of you may have vested interest in certain types of faulting based on what you're working on for your grad projects and stuff like that. So we can discuss that. So yeah, we tried to spread it out a little bit.